Hello again, everyone. In this video, we are going to see another solution of problem 3. And the solution is a bit different than the first solution we saw. So before we proceed, all the notations that we had before, including the notations about the bisectors, such as like little a, b, angles alpha and beta are preserved. And also for this problem, we're going to need to say that, for example, the angle beta is equal to 2 phi. So here is the angle phi, here's the bisector. Okay, another piece of notation, when for all these bisector A, B, C, D, E, we write little b vector for the unit vector on line B that points towards the center of the hexagon. So just to illustrate here, this tiny unit vector, this is our little vector B. Okay, another thing which we learned from the first solution was that, for example, the angle between A and B, the bisectors, is 60 degrees, and the angle between bisectors, let's say B and D, is 120. So if we draw those bisectors, let's say A, B, this angle here is 60 degrees, and if you draw this bisector and this one, this angle here is 120 degrees. So we can see that the bisectors A and B are parallel. Similarly, B and E are parallel, and F and C are parallel. So let's just write that down. So A is parallel to B, is parallel to E, and C is parallel to F, which, with our notation from here, also means that, for example, B vector is minus E vector. Okay, so now what are we going to do in this solution? We're going to prove that, given the angle relations for the hexagon, the condition that those three bisectors are concurrent is equivalent to another condition, which is completely symmetric for that construction, which in turn it will give us that if these are concurrent, then the other three are concurrent. So what is that relation? We are going to prove. So A, C, E, if and only if AB plus CD plus EF is equal to BC plus DE plus FA. Okay, so we're going to start with the assumption that A, C, and E are not concurrent, and let's just intersect them. So as I've intersected them in here, A intersected with C, here it is M1, C intersected with E is M2, and E intersected with A is M3. So M1 intersected with C, M2 intersected with A. We also know that all these angles are 60 degrees from, for example, just like this angle here is 120, therefore it's minus 60. So we have that the triangle M1, M2, M3 is equilateral. And say of side length little r. So we want to prove that r is 0 if and only if this happens, because r equals 0 corresponds to the case when the three bisectors are concurrent. Okay, let's start by looking at the vector bm1 and expressing it in two different ways. So bm1, first in this triangle, is BA plus AM1. And in this triangle is BC plus CM1. Let's rewrite this. This will give us that BA minus BC is equal to CM1 minus AM1 vectors. But also we know that B vector is equal to minus E vector. And if we observe that if we multiply this vector by this vector, taking the dot product, we will get this side cosinus of phi, similarly in here. So we will multiply this relation by, on one side, the vector b, and the other side, the same vector, which is actually minus e, and see what we get. So we get that BA minus BC cos phi is equal to, now let's look at CM1 vector and E. Well, the angle between them is 120, therefore it gives minus 1/2, and with the sign it cancels. So it is CM1 minus AM1 times half. Great, so we obtain this expression by analyzing these two bisectors. We can do the same for all the other two, and we will get analogously CD minus DE cos phi. It is equal to EM2 minus CM2 times a half, and EF minus FA cos phi. It is equal to okay, so we have this intersection, M3 A minus M3 E. Great, so we're already in good shape, because if we add this inside, we obtain exactly this side minus that side. So let's just add these three expressions, and we get that AB plus CD plus EF minus BC minus DE minus FA cos phi. It is equal to, well, the sum of these expressions, but let's just pause and see what do we get. So we have a CM1 here minus a CM2 here. So let's just look on the picture. So we have CM1 minus CM2. So that expression depending on where M1 and M2 are placed with respect to each other, is going to be plus or minus R. Similarly for AM3 minus AM1 and AM2 minus EM2 minus M3E. So this is going to be just 1 over half plus minus R plus minus R plus minus R. Okay, so this happens in general. Now, the left-hand side is 0 if and only if this expression is 0, plus minus R, plus minus R, plus minus R. Because the cosines can't be 0, because we have a convex non-degenerate hexagon. So when is this expression 0? Well, if we change one of the signs here, we observe that we actually add or subtract 2r, which means that this expression is actually a integer multiple of r, and the parity of that integer never changes. So if we start, for example, with r plus r is 3, therefore it's always going to be an odd integer. So this is 0 if and only if r is 0. So in fact, we proved that this expression here is 0 if and only if r is 0, which means exactly that A, C, and E are concurrent. So we proved the equivalence relation. And as you can see, this expression is completely symmetric in A, C, E, and B, D, F. In other words, A, C, E do not play any different role than B, D, E would play. Therefore, this is the end of the proof.